Welcome back to the online computer vision lectures. This is the second lecture on cameras and images. So at the end of the last class, we were discussing about the f number, which is in fact defined as the ratio of focal length to the diameter of the clear aperture. So it is the way it is typically mentioned or represented is in this form f divided by a number here, where you could interpret this uh, as the diameter of the aperture itself, because this is how it is calculated. Assume that your focal length is 10 mm, this one which is there in the numerator, and let the diameter of the aperture is 5 mm. So f number is 2, but it is written as f over 2, which means you could think of it as, well, if you put the value of f here, for example, focal length, let's say you take 10 mm here and substitute here, what essentially you will be getting is the diameter. So f number, when it is represented in this format, you could interpret it as you are referring to the diameter of your clear aperture. So this is what you would see here. So f over 1.4, obviously this being in the denominator, as your denominator increases, your aperture would be decreasing. So what is the consequence of decreasing aperture? Of course, the light passing through it would be reducing, but that's not the primary thing. The primary thing, by the way, this is how you would have seen it, at least in digital SLR cameras or the earlier SLR cameras, where you would be having a control to adjust the aperture. So this is where I think we were concluding the earlier video lecture. So let me make it a bit more clear to you. Maybe I'll now present it in a slightly different way by first discussing about the depth of focus. So what it means by depth of focus. Depth of focus essentially tells you that, suppose your object is somewhere here. So what is the range before and after that, the range of values for which you have a reasonably clear picture? That's what is referred to as depth of field. It's not depth of focus, it's depth of field. So the most important consequence of the diameter of the aperture is on depth of focus. This you could observe here. Uh, like for example, when you have the first one, you could see here is having a large aperture case. This is having a large aperture, versus this is the case where you have a small aperture. What would happen here is, this is where you are getting the image plane is here, the lens is here, and here the image plane is here. You could see here that the allowable circle of confusion, hope you remember from the previous class, which would essentially make things blurred because rays coming from they are essentially diverging there. So you see here, for any point starting here before this would eventually end up slightly beyond this. That's where it converges. Similarly, the points which are there here would be converging before this. You could see here, even if I move it slightly here, of course we are looking in a one-dimensional kind 2D diagram here, but that you could see it would be a beam of cone coming there and passing. So that you could see, that's why when you take a slice there, it is going to give you a circle of confusion there, which we discussed in the previous class. You could see here, when the aperture is small, you would get reasonably good picture for a large range of variations of your object depth here. If you consider this from this as a reference point and that varying on both sides as the depth, you could capture large depth. This is referred to as, the right word for it is the depth of field. So when the diameter of your aperture is small, then you would be getting a large depth of field. So the same thing in a slightly different picture here. this is your small aperture here. So you see it as a 3D, you imagine from this 2D diagram where a cone of beam is coming. So that circle of confusion is relatively, if you fix it to a threshold on the radius of your circle of confusion, for this aperture, okay, when this is your depth of field, that is further increased here, while this was the earlier one, this is larger here. Same thing showing slightly different way. Now you could observe the same thing from this picture as well. The same scene has been captured with the same lens but adjusting this aperture. So you could notice here the depth of field is more here. So you could see not just that object, beyond that whatever in the background is also there, that also you could clearly see here. Whereas here, the aperture being very large, this is something, the whole thing got blurred there, because that is where it would be diverging. So it is there actually with respect to the object backside. So it converges before, and by the time it comes and falls on the image sensors, the time itself it is diverged, and that diversion is quite high because of this large aperture. So if you want to capture your portrait images, okay, where and by the way, you could also notice here the quality, the depth you could perceive here, and the focus here is much better. By the way, you could say, this is the aperture size you could see here, f by 5.6 and f by 3.2. So this is small aperture and this is of high aperture. Okay, suppose if you want to get a panoramic view of a scenery, you went to a mountain or a beach or a forest where you would like to capture the variability there all around, this is what you should perhaps prefer. On the other hand, there is a nice lion or an elephant for which you want to capture the image, that is what you want it to get highlighted. Okay, then this is how you would do that. You adjust your lens aperture in such a way, so you would essentially use here a large aperture, and here essentially f number with this relatively so small aperture, in other words. Another few pictures highlighting the same issue here. As you could see, as the number in the denominator increases, essentially the what would happen there, f by, so what's happening to the aperture diameter here as you move on here from left 1 2 3 4, what is happening to the aperture? Is it increasing or decreasing?
It's going down.
Decreasing.
Hmm? This
Decreasing.
is small aperture, correct. So if the aperture is decreasing, what should happen? Should depth of focus increase or decrease?
Depth of focus increases.
Right. That is why there is some trees, leaves are there. You put a camera before that, and that just that you could get it very clearly here when you have a large aperture, and otherwise you could capture a lot more background here. Another point, I'm sure if some of you had experience with SLR cameras, you would be knowing. Anyone does have any idea about what this number is here? So it's like, well, your aperture is decreasing here. For a small aperture, you need to let more light. So you are keeping it for 1 hour 15 seconds here. Okay, that should make sense, because your, does that make sense? Tell me that first. I'm not sure. So here, what is the case here? You have a small aperture, correct? You have a small aperture to let it go. So this is a kind of case like this. When you have a small aperture, you should capture, you need more light to get a good image. So that's why you would be increasing your shutter speed, or the amount of time you are let the light to pass through. Is that fine?
Uh, just a small question, sir.
Yes, sir.
Uh, why does exposure time actually matter? Because if you look at it in terms of speed of light,
Hmm.
it,
No,
it's
it
not
is
about the speed of light, right?
it is about the amount of light.
So the longer you expose the film to light,
Right,
then the
right.
more better it's captured.
That's right. That's right. You are right.
Yes, sir.
So you are letting more energy. Essentially, your sensors are working on the light energy. Energy is nothing but integral of that over time. That's what you have there on the sensor. So the way you could increase it is your integral over t, that t you increase that. That's the basic idea here.
Yes, sir.
Good. So this image we have seen, and yeah, see, there is some I think thrill and some fun in making such images if you have an SLR, but don't think of buying an SLR camera for making one or two such images. But if you have it, you should experiment with something like that. They are making a very nice use of this depth of field, where it is focused here, whatever the point we are looking at here, this point is somewhere here, and then you play with it, and you could bring such nice effects where you could really feel kind of a 3D effect kind of stuff very nicely on your object of interest. Okay, I just I'm not I didn't, sorry, keep track of the sources for it, but these are the images I captured, I took from while searching for these apertures, how I could illustrate this more clearly. When I was looking at, I come across these images. So let me quickly show you this. By the way, there is something else, as one of you are saying ISO. That's tells you about the sensitivity to the intensity that is falling on your sensors. Let's not go into that at this point of time, which is kept here constant. And in fact, you would be playing with both aperture and shutter speed, both of them. Well, this is f by 1.4 here, 5.6 here, 11 here, 22 here. So f by 22 means your aperture size has decreased. So you should have more depth of field, which you could observe here. Okay, same thing, but I just like the earlier images, but some other scene that we are seeing here. Similarly, shutter speed, your aperture size is small. So that time you, yeah, essentially in this case, they were maintaining the same shutter speed here, right? So usually for the same shutter speed and sensitivity to light, ideally it should look slightly less in, I think, intensity wise also we should see something there. But again, within which range, dynamic range is there. If the scene is having enough intensity illumination, that's good enough to have an impact on the sensors is also another thing. But one thing for sure we can observe here is larger one. You could see it very clearly. This object is in focus. What is in focus is limited here. As you're reducing that, what is in focus is the depth of field is increasing. This again another image I took from the same PDF that I come across. Sorry that I didn't made a note of the source for it. Here the guy is hitting these blocks that have been kept there. There are again, then shutter speed also has another aspects you should also analyze while you're taking into account the shutter speed. Essentially you are integrating over time to get the energy there. But if the object itself is moving, then you can't really afford to increase it too much, right? So it's, this blurring is not just because of the aperture now. This is also because perhaps the shutter speed is, the, you are keeping the shutter open for quite some time. So perhaps I would attribute even that which is in focus now could get blurred because of your shutter, you are keeping it, and that integration is happening. So everything, all the if you look at it in much less time frames, it's almost like averaging across all the images, equivalent impact you will have. On the other hand, very good this is 1 over 20. Okay, that's how much is that, 0.5 50 milliseconds or something, you compute that. This is 1 millisecond. If you keep it, you could see that's actually falling. But even when falling, this you could see very nicely. So this is a combination of understanding the technical knowledge and also some kind of skill, I think you would acquire, have provided one has a keen interest on that and then is excited about doing this. You could capture such nice pictures, okay, with an SLR, and you would be able to appreciate the values of this aperture, shutter speed, and all these parameters. Okay. Okay, if not, I would now in just take you through another important aspect of this cameras and images referred to as your field of view. Essentially, field of view tells you at which angle, to what angle you are capturing that image. Say, for example, here, this field of view is almost 180 degrees here. There is another lens for which this keeps on reducing here. And what is its relation with respect to, with respect to, uh, with respect to the focal length of your lens is what we are going to take a look at here. These are again, I borrowed these slides from Professor Aaron Bobbick's video lectures, so credit goes to him. Yeah, coming back. So you might have heard about this telemetric lens and all. Suppose if I want to capture something which is very far, do you think my focal length should be large or small? What's your thoughts about that?
We should have a large focal length.
That's right. That's right. So that's why even those people who are going for photography in the wild forest or into the mountains where they want to capture something very far, they really would be having with them a very big barrel of lenses there, which in fact they have high focal length lens, or they create an equal impact where they will, by adding one after the other, multiple lenses there. So as your focal length increases, your field of view, so don't that's very far, and when it's going very far, you could see that in terms of degrees that would come down. So for example, this has, when you have, this is where 17 mm, a lens of focal length 17 mm, 28 mm, 50 mm, 85 mm, and so on, they are keep on increasing. So from the same position they were taking the pictures. Here, when they are taking that for a 17 mm thing, this is what they got. Later, there is a boat here. Okay, as they are increasing the field of view, you could see here that angle, this angle keeps on reducing, but that's where you get it things focused there, right? So that's boat is there, that boat become much bigger here, you could see it more clearly here. Then 50 mm, much better. Okay, 85 mm, even better. And then 135 mm, you could it's kept in the same position. Okay, that's fixed on a tripod and they are taking that. And eventually 300 mm, you could focus to much more detail here. And then you could see even a person on the boat with 500 mm. I assume that as 1000 mm from here. Okay, so 1000 mm, that means that very large thing, you are able to see only your field of view is 2.5 degrees there, that's got focused. So you could already interpret or understand here, infer here, that even a slight tilt or slight change in its position would focus you on somewhere else. You won't be able to see this guy standing there who is probably riding the ship, or somebody attending the ship there. You won't be able to see that, will completely switch to some other place even far away from the boat. So that's why it is said that they would be using tripods, not just because it's heavy because of all those lenses, but even a small tilt in your position would take you somewhere else. And the message here is the field of view keeps on reducing as your focal length increases. That's the message here. And let's see that in more detail here, which tells you that this is essentially the relationship here. So if you call this as phi, this is your lens, and on your camera backside you are having that screen. Let this be d, the sensor, the length over which you are capturing that image, that length be d. So this is essentially d by 2, and this that is phi, this is also phi. You could write now tan phi equal to that's the focal length here, it's getting focused, so this is focal length f. So your tan phi equal to, here you write the tan phi there, equal to d by 2f here. So your phi equal to tan inverse of d by 2f. You could know here, as f keeps on increasing, this value would decrease. so is tan inverse, and so is the field of view. Is that clear? Any questions here about the relationship between the field of view and the focal length? You could notice last class and this class, we are looking at various parameters of this cameras and the way you are capturing it and the way you are modeling it and the relationship between the actual size of your object, the length, the focal length of the given lens, distance between the lens and image sensors, and depth of field where you could capture it more depth. And now you are looking at the field of view. So another thing where many a time we looks similar but not definitely similar, have different effect, is zooming and another is moving. So this all of us, even with our cell phone cameras, we are quite aware of it. Is suppose I want to take your image, one way is assume that I am standing far, okay, and also assume that I have a very good high resolution camera with me. So there I'm considering two scenarios. Scenario A, I stand far away from you. I'm taking your picture. I stand far away from you, but I zoom in. I take the picture and I have enough resolution. I just take your picture by zooming in. That's one thing. Scenario two, I will come closer to you and take a picture, and in such a way that in this picture you are of the same size as in the zoomed in version where I was standing far away from you. Are these two pictures going to look same?
If we move closer, our field of view is still the same.
Doesn't matter, I'm finally taking a cropping of you after zooming. So I'm asking you, do you look same in both images? Case
No, but
A, I look far away and then take a picture and zoom in. Okay, don't worry about the resolution of my image. I have a very good, very high resolution image with me, good enough. Even if I zoom in, I get a good picture of you. Second case, I won't zoom in, but I stand close to you and take a picture such that a zoomed version size in terms of pixels, let's say, is same as here. I bring it to the same pixel number. So are they going to look same or are they going to differ? This is one such image where you had a large field of view, okay, and then small f, and another is small field of view and large value of focal length, and you take the picture. I hope everybody agrees that the car looks differently in both the ones. Do you feel so, or don't you think so? Hmm? The dimensions of the car look slightly different in both. If you can't make it out, this should help you. These images, again, he has taken from web and the link is there. I copied from him. So you see here, the focal length is kept on increasing. So the focal length is kept on increasing means what it is something. Is it increasing or decreasing, by the way? 350 mm, 250, I made an exactly opposite statement here. 350 mm, 230 mm, 200 mm, 135 and so on, it came to 19 mm. Okay, so for that small focal length, to get it, what I should do is I will come closer to you and take the picture. This is somewhere when my focal length is very high, I'll be far and taking that. So I could always adjust my zoom in and zoom out in such a way that the same field of view is there. I hope everybody would agree that first image doesn't look same as the second image. Or don't you see any differences in both the images? I'm sure you see that, right? What is it that is causing this problem? Can you make any guess on why this effect? Now if you can't still make that, you just see it. At least this animation should help you. This again I borrowed from somewhere else that I don't remember, sorry for that. The say, don't think that he changed his hairstyle or that. It's just that you could see with which focal length he had taken those pictures. You could see here, you could capture the same thing here, but depending on how far your camera is and the focal length, things could change a lot. Okay, the appearances could change a lot. And if you again notice next time the specs very carefully, the specs are given in such a way that, let's say, in and around 10 feet of distance, if I am observing you while you are standing around 10 to maybe 10 to 15 feet distance, how you appear, your photo should appear in that way. So that's how they would be capture. You are expected to capture the image because that is the distance at which we with our eyes will be observing a person, and the photo should be in that manner. Otherwise you could manipulate things in such a way that it's very sometimes it could become very complicated or a bit more tough task to identify that person accurately. So this is because of, this is referred to as perspective projection. See, you have a 3D object and you are taking projections of that object on a 2D plane. So depending on, you might be keeping the same object of your interest while you are moving by zooming in, zooming out, and keeping that field of view and changing your focal length. But the projection while you are taking it, when the things, when your camera is closer versus far, that projection of that 3D object could be changing. Say for example here, this is the case where your focal length is increasing. So at a very small focal length, this is actually the original object is a square, a cube that you are taking. But when your object is closer to your camera, what would happen if you just extend these lines, which are the edges of the cube? In reality, yeah, in the 3D world, what is going to happen? Where are they going to converge?
They will not converge.
Right, they don't intersect because they are parallel lines. But you take that picture a close, then it looks like all of them would converge here. So that's are going to intersect here, even the parallel lines. But when your focal length is large, when you are far away, this slowly become parallel. When you are taking the picture from a farther distance by increasing your focal length, then it appears, then they come more close to the reality. The same thing, even this is again is taken from this textbook, Chesterman and Hartley. You could see here, these are in fact parallel lines. Okay, nobody would build a house where the things would be intersecting or coming down. Hopefully not, because your floor size, different room sizes itself would look pretty strange unless he is having some other design reasons there. You could see here, when this is captured closer, you could see here they look as if you extend these lines, it looks as if they are going to intersect, right? So whereas this, you would see that effect got reduced as you are increasing your focal length, because essentially a 3D object's projection on a 2D plane is what you are looking at the moment you have a 2D image. And this is referred to as perspective projection. Perspective means from some viewpoint, you are taking a 2D projection of a 2D object. So you are having just one perspective of that, okay, to say it in loose terms. So that's why it is referred to as perspective projections. Okay, so just would like to conclude this discussion about cameras and images with some very interesting cinematic effects that have been created with that. And in fact, the credit goes to to use it in a very entertaining or engrossing way goes to the director Alfred Hitchcock. Hope some of you would have seen his movies. Let me show you this. Alfred Hitchcock made very suspense thrillers quite a lot in 50s. Okay, very popular. And he had used this effect of same scene, you come closer to it. Now what you should do is, you want the object of your interest to be of same size, so you zoom out, you go much closer. Okay, now you want that same person to be of the same size, again you zoom out your camera. But notice here, the effect of perspective projection would give you different images just like this. So he is the one who pioneered or who used this effect for the first time in movies, which I would play now. impact of what you feel when your head is, we call my head is rotating. That's how we say informally, right? So when that impact he has it, he had actually fallen in couple of times in a hotel. So that effect he brought it here. There when we take down. So basically he wanted to save, I think I have, by the way, I haven't seen myself, but it looks like he wanted to save him, but he has the effect of vertigo. That's the problem, he has it. And that's why he could not follow her up. And that effect, if you notice, he has nicely shown by looking at it, the scene would remain same, but that's where he moves his camera. Okay, that's effect is known as Dolly Zoom. See that effect. The object would remain same. And this is the first known movie that they used it. And then there are even quite a few places where it has been used. Okay, that's also where you could see the shape. If you notice, the size of those guys would remain same, but it will give you a slightly different impact camera when you look at it, because the field of view is changed, but the zoom in and zoom out is something done in such a way that they appear to be of the same size. Okay, one last thing I would show you before I conclude. I would skip some.
The Dolly Zoom was also used in Martin Scorsese's 1990 film Goodfellas. In this portion of perspective, Vertigo, who developed it with Hitchcock unit cameraman. According to legend, Alfred Hitchcock got this idea when he fainted at a party, and it was Paramount second unit cameraman Urban Roberts who developed it with Hitchcock for the film Vertigo. Since Vertigo, the Dolly Zoom has been used in many other productions, including by Hitchcock himself in Marnie. Steven Spielberg utilizes this effect in Jaws in 1975. This sudden distortion of perspective isolates and zeroes in on Brody. His worst fears have become real. They should have closed the beach. The Dolly Zoom was also used in Martin Scorsese's 1990 film Goodfellas. In this conversation between Ray Liotta and Robert De Niro, everything seems normal on the surface, but the Dolly Zoom emphasizes that the world is slowly changing around them.
He took the booth near the window so he could see everyone who drove up to the restaurant. He wanted to make sure I wasn't tailed. He was jumpy. He hadn't touched a thing. On the surface, of course, everything was supposed to be fine. We were supposed to be discussing my case, but I had the feeling Jimmy was trying to sense whether I was going to rat him out to save my neck.
Henry has just come to the realization that his best friend has just put a hit on him, and there really are no Goodfellas in the life of crime. So why does the Dolly Zoom work? Well, it all boils down to the basics of photography. We're taking a three-dimensional world and reducing it to a two-dimensional image. So let's imagine a camera obscura, the most basic type of camera, a pinhole camera. We have a subject, an aperture, and an imaging plane. The light rays from the subject travel through the aperture in a straight line and onto the imaging plane. Now, if we draw a straight line from each edge of the image plane back out through the aperture, we can construct an angle. This angle is our field of view. With a pinhole camera, there's no way to increase or decrease our field of view without moving the image plane. But we can use lenses with different focal lengths or zoom power to bend the light as it enters the camera. And now we can see more of what's around, get a wider field of view with a wide angle lens, or zoom in closer with a narrower field of view with a telephoto lens. By bending the light, though, we introduce a phenomenon called perspective distortion, which is the warping of objects based on the distance from the camera. Now, perspective distortion doesn't change simply by increasing or decreasing the focal length or zoom. If I sit here with a camera, zoom all the way in, I'm not going to notice a shifting of perspective. But it does change based on the relative position of the camera to the subject. Compare these two shots. The left is a zoom in, while the right is a dolly in. The zoom in shot just magnifies the image. In the dolly in shot, the surrounding objects are affected by the changing perspective distortion caused by the camera movement. And this is how the magic of the dolly zoom works. We increase the focal length, we zoom in, as we simultaneously dolly the camera out, or vice versa, we dolly in and zoom out. The zoom keeps the frame crop the same, so the foreground element stays roughly the same size throughout the move. This isolates the effect of the perspective distortion caused by the movement of the camera. And this shifting of perspective distortion is what creates the effect of the dolly zoom. Theory is all well and good, but it takes a little bit of effort to actually get a decent dolly zoom in production. You're going to need two things, a dolly and a zoom. Well, that should be pretty obvious. You can try to do it with a slider, but you might run into the problem of having the slider get in your shot, and that's not good. I have done it with a slider, you're just more limited. As far as the zoom goes, you really need to have a camera with a smooth zoom, preferably a motorized servo-controlled zoom. It's nearly impossible to pull it off with a photography lens unless you're shooting stop motion. After all, that's why it took them till 1958 to achieve this effect. They needed a smooth mechanical lens in order to pull it off. Now, to demonstrate, I have a cutout of Maestro himself, Mr. Alfred Hitchcock. I'll start the shot dollied all the way in and zoomed out. I'll keep the aperture stopped down so I get a deep depth of field so I'm not fighting with the focus during this move. Now, as I move the dolly out, I will carefully zoom in at the same time, trying to match the speed of the zoom with the speed of the dolly. If I want the opposite effect, I'll dolly in from my final position while zooming out. Either way, I like to start with the dolly all the way in because I'm limited more by my wide angle than I am by my telephoto. Getting this effect takes a lot of practice to get just right, as the speed which you need to dolly and zoom will change depending on where you are in your focal length range. Just keep doing the shot over and over again until you get something that you're happy with. Just realize it does take a little.
Yeah, that's about the dolly zoom. This effect is known as dolly zoom, where this should tell us about the perspective projections impact there versus the focal length as well, where from your zooming in effect. So any questions on this? I think, yeah, that's rest I would leave it because the message has been conveyed. Well, so far we have seen things like a simple thin lens is what we have considered, but in reality, lenses are not thin, lenses are not perfect, okay? And sensing arrays are reasonably good in that aspect. Photographers are, again, I'm just snatching the slide from him. Photographers are perfect, except some of us, he says nicely. And there are a lot of issues that needs to be addressed in reality when you are using lenses for capturing the images. For example, ideally you would expect something like this, but when you use a specific lens, there could be geometric distortions that are coming into play. For example, this could come something like this, which is referred to as pin cushion. So the grid this way, when you are capturing that, you would get something like this, or depending on the type of lens you are using, you would be getting something like this. So these are referred to as radial distortions of the image. They are caused by the imperfect lenses. Deviations are almost noticeable for rays that pass through the edge of the lens. So this is, for example, the original image captured, but then if you tell the lens what is your exact the lens details, it will have some unique number to identify. Even your Photoshop nowadays, it's not just SLRs, you have digital SLRs, so they do the correction within themselves and give it to you. So this what captured is this, and then once you mathematically model that and apply the required transformation, then you would get what you in fact desired. They do it sometimes purposefully also because they want to increase the field of view, and later with the same lens specifications, and later they would be applying the transformation to get the right image. That's one kind of distortions that you would get with lenses. Another kind of thing that you get in reality is chromatic aberrations. You all know the light which we are seeing as white light in fact has this VIBGR distinctions. So each one is having a slightly different wavelength. Because of that, what would happen when it passes through the lens, these lights within the white light, the green, blue, red, all of them would converge at different point. So because of that, you would be again getting some undesirable artifacts in your image. For example, you see the image here. Originally, it's just a blue light, white light, and then there is this green plant here. But when you take an image with a lens, what you get is also a red light here. This is coming because particularly at the edges, because of this chromatic aberration that's happening. Again, these days, your DSLR cameras itself would account for it, or else you have in Photoshop, again, you have a lot of options that you could explore in order to get rid of chromatic aberration. Another important effects that needs to be considered are very important effect. A critical thing that one has to consider is vignetting. Okay, maybe some of you might have heard this name. Vignetting is where you see less light around the corners of your image. So this effect is known, I don't know why I initially thought it should be vignetting, something like that. But the way when I checked the pronunciation, I think the UK and US pronunciation for this is vignetting. Maybe that comes from word, I don't know where it comes from. That's how it is pronounced, vignetting. Okay, so the reason for that is, you in practice you would never use in fact a single lens. You would be using a sequence of lenses in order to get the kind of effect that you would require, or to reach the kind of specifications that you desire. So then what would happen is, consider an object here. There is lens 1 here, lens 2 here. The light which is falling here at this point, this part of this light will not in fact go to the lens and reach the object here. This would be going away, because at the particularly at the boundaries of your object, and that's why you have less light there, and that information part, that particular region is not there. So usually in the images that you are capturing, you'd be getting something like that region getting blocked out. Okay, so that again, you just Google vignetting and you will see a lot more images illustrating this effect. Okay, so that's reason being, some light misses the lens, or it is otherwise blocked by parts of the lens. That's what the effect is. Okay, now everything is good in a classroom where you just discuss about a thin lens there, but in practice this is again a slide, very old slide, but still good enough. Some 2470 mm zoom Nikon lens, that's I think you could figure it out there. They will not be now, thanks to the technology. It's not just the convex lenses that you could get. You could get quite a few shapes of lenses depending on your requirement. You could engineer them in quite a different ways now with the help of the technology. So in fact, if you take this Nikon lens system, it's a sequence of 15 lenses that you have it, and the arrangement, there is a whole lot of technology involved here, engineering involved here, where you would try to, while capturing itself, would try to compensate for some of the effects, like it could be, for example, chromatic aberration, it could be, for example, radial distortion, or many other such effects. So they will be of different sizes, shapes, materials if required, and it's never a single lens. That's the amount of complexity that you would find out in the recent lens systems. Okay, so however, you don't have to worry about all these things. Again, a slide from R.N. Bobbick, he would say it's a retreat to the academia, because we will assume just a pinhole model and go ahead with it. No distortions in our courses and no aberrations at all. So that makes our life easier. Okay, so with that, I would conclude the discussion about cameras and images. And then you already had now a bit of look into this perspective projection. This is something maybe for next 1 or 2 classes we are going to discuss about perspective projection in more detail. That's what we will do for the next couple of classes perhaps. Any questions so far? Hope you got some idea about cameras and images. So usually you would find courses itself, a full course dedicated to cameras and images itself. That's not something we can afford, but at least I wanted to give you some flavor of it, giving you some idea about what is this F number, what is this field of view, what is the depth of field, what is and all those things. So that's why we discussed these points in just a couple of classes. Yeah, any questions? let's sign out now and see you in the next class. Bye. So we are going to discuss about perspective projection. Okay, right. Bye. Take care.